Okay, it's 1 minute after, so it looks like we have a quorum. One of the things I just want to thank everybody for their attendance here today. Um, this is a special talk. One of the things that's really key here is the manufacturability of components, and this talk focuses on some of the lessons learned with respect to making mirrors for the James Webb Space Telescope. And I'm going to introduce Glen Cole, and I will just turn it over to him at this point. It's all you, Glenn.
Okay, thank you very much. I'm really glad to be able to share the story. We touched infinity, that is the JWST mirror makers. How many of you are following the incredible James Webb Space Telescope? Well, I think we can all agree that it's truly a marvel, and it is just now revealing the cosmos like never before. But have you ever wondered how the heart of the telescope, its mirrors, were created? Now imagine taking a behind the scenes look, and that's just what we're going to do today. I will share the incredible story, both the beauty and the challenges of JWST mirror making, something you will not find anywhere else. Hello, my name is Glen Cole. I'm a tool maker. Specifically, I make telescope mirrors. For the last 40 years, I have helped create some of the world's greatest telescopes. As I like to say, I'm not Carl Sagan or Stephen Hawking, but I did make their telescopes. If I may share an analogy, the astronomers are the race car drivers, and we built their Formula One beauty. We are the enablers of their amazing science. On James Webb, I was the chief engineer for mirror polishing, and here is our story. First, a bit of a disclaimer. The presentation is based on a true story and actual events and was drawn from various sources, including my flawed memory and the published monthly status reports for JWST mirror polishing. All of the personnel captured in the shop photographs were photoshopped to protect their identity altogether. I invented the character names. The cartoons help illustrate the story in a humorous fashion and in graphical form. The presentation contains fictionalized scenes, composite and representative characters, and dialogue for dramatic purposes and narrative purposes. Anyway, it's a true story. And yes, this is a story about the mirror makers of JWST, but as your guide, a bit of my history is shown on this page. It all started 40 years ago with the system shown in the upper left. This was my first job with my father, also a mirror maker, and we worked with Dr. Charles Townes, the Nobel laureate and co-inventor of the laser. We polished the 2-meter flats and the 1.65-meter parabolas for 2 of the 3 systems shown here. These are also known as infrared spatial interferometers. Further, you can see my mirror making work on the dark side in the lower left. These systems employed large light-weighted glass mirrors. And we also see the SALT, the South African Large Telescope, a multi-segmented telescope in the center. And of course, foremost on my mind, the James Webb Space Telescope. In preparation for Webb, there was what we call the AMSD, that is the Advanced Mirror System Demonstrator. And this was a competition of telescope architectures. Central within the architecture were the telescope mirror segment designs. I was working at Eastman Kodak at the time, and on the left, you see our beautiful entry. This is a low temperature fused glass honeycomb sandwich mirror. The material is a Corning ULE, that's a titania doped fused silica, what we call a zero coefficient glass. And it was a real work of art just in the creation of the blank alone, even before the polishing. And on the right, we can see the competing mirror, an open back light-weighted beryllium substrate. The engineer gives you a sense of the scale of the segments. This was also quite involved, just in creating the substrate. prior to any polishing activity. And the winning design was the ball beryllium approach. And this was as exciting for some as it was devastating for others. In the central performance box, for the nerds amongst us, and there's probably a few here, we can see the earth-shattering specifications, not for the faint of heart. So with that, I was fortunate enough to be selected to lead the polishing team out west, and soon found myself as the chief engineer in charge of beryllium mirror polishing out at what I will call Thompson Freeform. Yes, I transitioned from one team to the other and to the beautiful and complex world of beryllium mirror polishing. And the early days at Thompson were what I call the good old days. We had a lot of work ahead of us in what we called the facilitization. Not only did we need to create a custom polishing facility, we needed to create all of the equipment and tooling as well. That is polishing machines, measuring equipment, handling systems, etc. And here we see the proud parents taking baby Webb for a stroll around the block, and the neighbor asked for a better look at baby Webb, and wow, is he surprised. Yes, folks, I don't get out much. And here we see the details relative to the primary mirror, and you can see that it's consisted of 18 hexagonal segments, and there are 3 unique, as we call them, prescriptions or surface shapes defining that or making up that parent. So we have a type A, there's a type B, and a type C. And there's just a few millimeters of gap between those beautiful beryllium segments. We also see some of the ways we describe the surface errors in terms of surface frequency. We've got the mid spatial, as we call them, requirements of 20 nanometers or better, high spatial, and of course surface roughness. And after a solid year and a half, we were able to call the facility complete. And this was a big affair, with all of our tiered partners from Ball to Northrop and NASA attending the dedication. And it was a proud moment for a job well done. Our team had really outdone ourselves and created a top-notch, dedicated optical shop specific to JWST. But as we would find out later, there were still many nuances in direct beryllium polishing that stood between us and the finish line. And here we have a look at our 7 large polishing machines, and these beasts were created specifically for Webb. We started with a large machine center base and then outfitted it with a variety of proprietary grinding and polishing heads. The upper photo is a close-up of one of the polishing machines. That is our what we called LCP01, our first machine, the granddaddy of them all. And the lower photo shows the large optical shop. And from there, you can see all 7 machines sort of between here and the metrology room at the far end. And you can also see what we call the command center, sort of in that lower photo where next to the American flag. And my desk was out there with the process engineers right there at the command center. And the mirrors are, of course, made of beryllium. That's the 4th element in the periodic table. So it's an amazing thing if you look at the periodic table. And this was specifically 030 beryllium, and it was specifically formulated for the Webb mirrors. And it represented a step forward in terms of material properties. It was, at the time at least, the most isotropic beryllium type that had been made at the time. The boules, as we call them, were created by hipping, and in this process, beryllium powder is placed in a container where heat and pressure are applied in what resembles what I think of as sintering, of course different, but similar. After creation of the 030 material boules, the CTE was it's an interesting thing for this material that the CTE, or the coefficient of thermal expansion, asymptotically goes towards zero at the in-use temperature of 40 Kelvin. That's 40 above 40 absolute zero. The room temperature CTE, of course, was not very good. But as the temperature, as I said, as the temperature goes down towards the cryo temperatures, the CTE also approaches zero. And after the bulk of the material was removed, as shown here, looking at that open back rib structure, the blank was what we call a 90% lightweight. Now, we had strict beryllium protocols, and we even hired a beryllium safety officer to assist in keeping us all safe. We had periodic blood tests to look at the leading indicators of what we call beryliosis, and we also wore protective equipment, or PPEs, during certain risky operations. In the cartoon on the left, we see, well, this is actually not funny. This actually is a cartoon, but it actually happened. One time, we remember vividly, that everybody does, the blood samples were, quote, lost in the mail. And of course, we can see in the cartoon, I was not a happy camper. Nobody seemed to like to give the 3 vials of blood a second time, but that's exactly what we needed to do in order to be able to be safe and to monitor the beryllium exposure. And the cartoon on the right is another thing that I actually overheard, as one day I was walking past what we call the smoke hut, and I thought it was quite entertaining when one of the guys said, you really should consider, double gloves, 2 gloves on top of each other during the cleanups, dude, because of the beryllium. And the other guy taking a drag on the cigarette says, well, you do realize there's more beryllium in your cigarette than in the entire shop. So smoking's pretty risky. We were pretty safe in the shop. And another thing about beryllium, and these are all some of the challenges that were in front of us and that we had to overcome, frankly, was the fear of what we call pitting. And that hung over our heads really for the duration of the project. Because with direct polishing of beryllium, there's a risk of pitting depending on the chemistry slurry. And our greatest fear was that if there were too many pits, that we would have to basically start over with our optical fabrication and go back to the grind. And nobody wanted to do that. In the center image, we see our Keon's microscope system. And with this, we could characterize the pits, if any, and return precisely after the next run to look at the progression of the pit, or basically to monitor things as needed. The actual pits were very small and infrequent, but we were vigilant in their status and resolution because, as I mentioned earlier, in the hipping process, the powder, it was hipped together, but of course there was a minuscule amount, less than 0.5% of beryllium oxide on the grain boundaries that would sometimes be attacked if the chemistry was a little bit out of bounds. And it is a tricky material. Of course, the details are proprietary, but let me simply say that if the slurry is too strong, then we were at risk, as I mentioned, for pitting. And if the chemistry was too weak, then the removal rate slowed down enormously. So there was always this nagging temptation to mess with the slurry. And the cartoon illustrates the dilemma. Here we see my lead process engineer. I'll call him Norbert. His name's something different than that. And he was always right. He always wanted to adjust the chemistry so we'd get good removal. But that was also risky in terms of the risk of pitting. So we had to walk that tightrope. And in this photo, this is an interesting and unusual photo. We see what we call the tertiary. So there's not just primaries, but there's also, of course, a secondary and a tertiary mirror, all beryllium, materials. And here we used a dye penetrant inspection to see if we might be able to get a better look at any possible pitting on what we call the TM, the tertiary. And even though we tried this. The pits were so small, if any, that it didn't actually help us that much. And amongst all the hard work, there was an occasional light moment. And to preface, let me say that, first of all, I don't get out much. And second, I'm starved for entertainment. So the pitting situation was the perfect setup for asking the new process engineer for some beryllium putty. But let me be clear. There is no beryllium putty. Only the opportunity to ask for the putty to fill the surface pits in segment A6. So that was fun for us, but we never came up with the beryllium putty. That was just a dream. And the EDU, that is the Engineering Development Unit, and it was really the workhorse for process development and refinement. The idea was that the EDU would lead all of the other flights, what we call flight segments, by 6 weeks. And this EDU buffer, as we called it, would help reduce the risk to the flight segments. The problem was the EDU also hit all of the unexpected potholes along the journey. So the EDU was the process pathfinder, but it was always needing adjustments as it progressed. Over time, the EDU buffer was reduced to 2 weeks, and there was always pressure to keep it as the leader of the pack. And it was a type A segment, just for reference. In optical fabrication, the early removal steps are typically grinding steps, and the incoming surface figures of our blanks were on the order of, say, 100 microns different from the prescriptive shape. With grinding, we would refine the shape. In the case of the EDU, we also discovered just how much residual stress was in the blank itself from the very beginning. So we knew that the blanks would come to us with this residual stress, and we knew that it would be in excess of what we call the micro yield limit, and be a problem in terms of long-term stability. What we didn't realize is just how much stress was really part of the blanks as we received them. So the processing time needed to address this residual stress, and that was a huge issue. We spent a huge amount of time addressing this, and it was not originally planned for, as I mentioned, and the subsequent segments would go through a very significant amount of what we call thermal cryocycling in the beginning, just to make things a little bit more stable for us. So this is, again, addressing this micro yield limit in this beryllium. So the beryllium has a lot of amazing properties, but it has these challenges that I'm mentioning as we go.
Glenn?
Yes.
I'd like to add a word on this. If it's
let me give a quick introduction. Lester Cohen was a colleague, extremely helpful, super helpful on this, and he was always there with us, shoulder to shoulder, solving problems. And yes, we're glad. Go ahead, Lester.
So when the segments come from the Axis company in Alabama, there's residual stress in the surface due to all of the machining that Axis had done. And that stress over a long period of time, the life of the telescope will actually creep out and change the figure. So what Glenn and company had to do was to remove a certain amount of the surface in a uniform fashion to reduce that stress, so that over the life of the telescope, the figure would not change more than what was currently in the error budget, which might have been on the order of 5 nanometers. Thank you.
Exactly. Yes. Yeah. Like I said, Lester was a huge power, and he helped us tremendously. And I appreciate that to this day, Lester. Yeah, but we are trying to make surfaces that look good at cryogenic temperatures, and they need to be stable. And so if we have this internal stress, the material, as beautiful as it is, it's got to be stable. And so we had to work through this and minimize or basically eliminate it within the air budget so that we had stable surfaces that we wanted. And here in optical fabrication, I want to just mention we iterate between surface figuring and surface measurements. And here we see one of our 3 coordinate measuring machines, or CMMs, which we use throughout the fabrication process. We captured both the mirror substrate stability due to micro yield, as we just mentioned, and what we call also the surface figure or shape of the mirror. And here is an interesting perspective on that same CMM, but we're kind of have a nice perspective. We can see the open back rib structure. As you could see, it's very stiff, but of course it's very lightweight, and it has a lot of machine pockets in the back, open back rib structure for these segments. And here in the central image, we show 2 different ways of visualizing the surface figure, or that is comparing the shape to the desired prescription, as we call it. The colored image shows a relative height according to a color bar on the right there, the reds being highs and the blues being lows. Another way to look at the same figure is shown on the left, and this is what we call an interferogram, where points along the fringes or lines are the same relative height. In addition, we can see some interesting features shown here in this interferogram. We see these small dots, or quilts, as we call them. And these are the unsupported areas between ribs, and with the polishing pressure, you can imagine that these areas are slightly depressed during polishing. The pressure would push those unsupported areas away, and as the tool is removed, of course, they would naturally elastically spring back and present some bumps that we call quilts. Now, of course, these are gone. They're not up there at the Lagrange 2 point as we speak. These quilts were removed and polished away. And one critical, but as we mentioned, misunderstood property was that of what we call micro yield. And basically, if you stress the beryllium beyond the micro yield, the substrate would be unstable over time. And this stress would slowly be released, and the instability would last for years, literally years or more. So it's something, again, that we had to work through. And for us, the stability, of course, was key. And the remedy was what we call cryothermal cycling. The stresses could be reduced and managed with the application of the proper cycle, that is heating and cooling. And of course, the details are proprietary. Here we see a segment on a cryo carriage being loaded into the chamber. They run, typically the runs were about 2 days in the chamber. And in spite of our normal 24/5 operations for polishing, we would actually run these cycles after we got confident. We would run these over the weekend. And we knew before the contract was awarded that the thermal cycling was needed, but what was not known to us, really to anybody, was just how much was needed and how much stress they carried, as we mentioned from the very beginning. What was also not appreciated until the EDU progressed was, even in loose abrasive grinding operations, the surface stresses required cycling. So even just a normal loose abrasive grind, your local stresses in the surface exceeded the micro yield limit. And at first glance, this is a precarious picture, but let's back up a bit. In spite of the size, the blanks were easily lifted by 2 trained technicians, but the tricky part was avoiding touching the ribs on the back side. These are very thin ribs. We did practice plenty of times with our surrogate, mirror before, of course, prime hardware handling. There was also just limited people that were basically trained and certified for this kind of handling. In any case, we needed a safer approach for handling the segments. Note in this image, you can see a technician with a respirator and a PAM. The PAM is a personal air monitor. And in the beginning, we all wore PAMs to measure our beryllium exposure during the processes to see whether we need to adjust the process or whether we would have to employ some protection. So these PAMs, as we called them, had filters. The filters could be removed at the end of an operation and sent away and analyzed to see if if there was any detection of beryllium at all in the filter media. And yes, there was even occasions when we flipped mirrors by hand. Nothing bad ever happened, but shortly after we created some handling equipment, I'll show you in a minute, to perform these operations at reduced risk. And please note, the expressions on the operators' faces, that's not accurate. Remember, as I said earlier, all of the people here have been photoshopped. These are not anybody that I recognize, and nobody, believe me, nobody was smiling or enjoying a hand flip. And as I mentioned earlier, here we see what we call the fixture transfer station. And this allowed for a lot, in most cases, much safer handling of these valuable and somewhat fragile segments. We call this the fixture transfer station, or the FTS. This really became the hub of our handling system. And if, for instance, we needed to flip a segment, or we needed to, for instance, transfer from a standard carriage to what we call a cryo carriage, we would go to the FTS, or the fixture transfer station, to enable this at a lower risk. And one of these people is me, but the face has changed. And as I guess nobody said that beryllium wasn't messy. And here we clearly see the dark gray swarf, as we call it. This is waste material. It contains, of course, beryllium particles along with spent abrasive. And you also note the plastic skirting to help keep things manageable. And we spent an enormous amount of time cleaning after runs, whether it was grinding or polishing. And from a safety perspective, and this is a key point for safety, it was critical that we never let the swarf dry out. So our procedures ensured this. It was a way to keep the beryllium particles from becoming airborne and putting us at risk. So we never let things dry out, ever. And that would keep us safer so that they wouldn't become airborne particles that could get into our airways. And the cleaning was always, almost always, a two-person affair. And you can see in the photographs, it was manageable, and it also saved our backs to have a little help on these operations. These segments, maybe they don't look too big to you, but when you're cleaning them, as shown here, they're pretty big. And of course, we had to keep track of all the white materials, and the wash liquid all had to be disposed of per our beryllium protocols. And the process engineers were in charge of interpreting the metrology surface data and creating what we call run files, whether it was grinding or polishing. And we, myself included, worked out of as I mentioned earlier, the command center. And this was rather central to the polishing machines and to the metrology room. And one day, midway through the program, we had a visit from the chief scientist of Webb, and he opened up with an impromptu speech with plenty of praise for the creation of the Webb's mirrors. But he also shared what kept him up at night. And he said he feared that the 5-layered sun shield might malfunction and make it a moot point of how fantastic our beryllium mirrors were. And he said, I worry about something much simpler than the mirrors, the sun shield. Even though it's simpler, it's still critical to our mission. If the sun shield malfunctions, as I remember him saying, your beautiful mirrors will be for naught. And he worried, we all worried about it, even in the process engineering group, about, maybe a cable would come off a pulley or something like that, and we'd have one big wrinkled mess a million miles from Earth. And I remember speaking to my senior process engineer, Norbert, and I told him to his face, and this is real, I told him I would go up and untangle, keep it nice, the darned sun shield myself if necessary. And he looked me in the eye and he said, no, you won't. You can't get back. We don't have the technology for a return trip. And I said, seriously, with passion, I would go up there, fix it, and I would float off into cryogenic space with a smile on my face. And I was serious, still serious. And just to reinforce what I mentioned earlier, the process engineers, there was a lot of things to account for in terms of risk, if you will. There was micro yields, there was pitting, we had edge roll to worry about, and all of these things we had to keep in mind as we went through our optical fabrication sequence. And here we see we got my process engineers walking the tightrope, and of course they're creating run files, and they got to keep all this in mind. So it was a precarious dance for sure. And as I mentioned, the direct polishing of beryllium requires a lot of finesse, and the slurry details were important, again, to balance the removal rate with the risk of pitting. And here we see the preparation for the start of what we call a smooth out polishing run. So there's different types of polishing. We had figure polishing. Here we have smooth out polishing. We interleave those two to give us the surface figure that we needed, figured and smooth. And here you can see, and it's just really a nice picture, the beryllium really polished up nice. Of course, eventually the segments to give us good science would need to be gold coated. But it was beautiful to see once we got a good polish on the beryllium. And as I alluded to, and this is very important, the Webb operates at Lagrange 2, and that's roughly 40 Kelvin. And for reference, liquid nitrogen, it's really cold, right? But it's at 77 Kelvin. So this is colder than liquid nitrogen. And we, of course, made the mirrors at room temperature, but we needed them to look good. Final figure, they have to look good at 40 Kelvin. So after the initial polishing, the segments were shipped to the XRCF cryogenic chamber to establish what we call the cryo backout. In other words, we needed to account for the surface figure change due to cryogenic temperatures. And here we see an example, I believe it's the EDU, at room temperature that at 293 Kelvin, the surface figure is shown in the left-hand figure. It's about 103 nanometers RMS, not great, but after cryo figuring, the segment was taken down to 40. The same surface, the same surface here, the surface was about 20 nanometers RMS. Again, same surface, two different temperatures. The other thing to remember, and this is also key, each individual segment had its own segment-specific cryo backout. So none of the segments had the same cryo backout. They all changed differently when they went from room to cryo. We had to account for that. So they didn't look that great at room temperature. Here, this segment would have been 103 nanometers, which of course is not good enough. But when you take it down to cryo, it gets quite good. So that was one of the main challenges, is understanding through measurement the cryo backout and using that backout in making segments so that when the segments actually went down to cryo, they would look as the prescription required. And another concern was edges. And the blanks were hexagonal. We received them as hexagons. And the edge relief was a scant 5 millimeters. What do I mean? the difference between the distance, I should say, from the bevel to the clear aperture was 5 millimeters. So the surface needed to be good out to better than that. So the edge, if we had rolled edges, we had to make it a very small effect. So we were everything's great until you roll the edge, and the challenge in optical fab is that if you roll the edge, the entire central region would have to be pistoned down to recover it. So we always kept a close eye. It's proprietary, of course, but we always had to keep a very close eye on those edges. There's lots of ways of dealing with edges, but this is tricky. And the metrologists, or the map makers, if you will, they used the CMM, what we call the Shack-Hartman, and the optical test set to measure the mirror surfaces. And based on their measurements, the process engineers would, of course, decide how to hit or how to create a run file for that next run. And there was always a bit of mystique associated with the metrologists. And as you can see by the cartoon, they didn't actually need a Ouija board or a crystal ball, but there was a lot of subtleties. The cryo back out, as I mentioned, gravity back out, yes, and test set back out are some examples. So all of these back outs had to be applied so that these segments look good in L2, at the L2. And here we have a bird's eye view of the optical test. And you can see that it's a CGH type test. So the CGH establishes the reference wavefront, if you will, and compares it with the test surface. And you can see here that the path is folded. So we got a fold flat at one end. And the whole thing is resting on these two enormous granite slabs. So there's a lot going on here, but this is our optical test. On the left, the segments would be arranged. I'll show you in a minute some more details. There is basically a 6 degree of freedom robot on the left side here to get the segments aligned. That is with the CGH, so that we get a good test. And here is, on the left, we see a clear image of a polished segment under test. And this is what I call the alignment robot end of the test set. And each of the 3 segment types, A, B, and C, required a specific 3-dimensional alignment in order to capture the optical test. It's really more than, I'm going to say 5 degrees of freedom. The CGH, computer-generated holograms, were a diffractive optical element used to establish the reference wavefront. This reference, as I said, was interfered with the light off the mirror surface, and the resulting interferogram was what the metrologists would put forward. And of course, from that, the process engineers would generate the next polishing run. And this gives you a little bit better look at the mirror under test, MUT as we called it. The positioner allows for movements, as I mentioned, in 6 degrees of freedom. And this photo was taken a bit early in the testing sequence. Of course, the body heat from the metrologist would be a big problem, but the actual test was about a half an hour later. So there's a lot of alignments and so forth. And, if as needed, we had, the metrology room had, laminar flow, and we had mixing fans, and as needed, we could get a good test on these segments.
Hey, Glenn.
Yes.
One comment, the picture that you're showing right now, because the beryllium at room temperature has an expansion coefficient of about 6 parts per million per C, they have to be extremely careful of the thermal environment that the mirror test set was in. And so
right.
they had to build a horizontal, basically a laminar flow facility
Yes.
that could keep the temperatures to very small fractions of a degree C, so that it wouldn't affect the figure of the mirror.
Yes, exactly right, Lester. The whole metrology lab was really built with this laminar flow. So we had a diffraction grate on one end, and that would be, if you will, on the right side was the exit of the airflow, and it would transit across the entire metrology room in laminar flow fashion. And we were able to control the temperature, and needed to, as Lester mentions, to control the temperature to a fraction of a degree C to give us these good tests. And here we see the Shack-Hartman, as we called it. This was a clever metrology tool that could measure the surface in the grind. And we used infrared light to measure subapertures of the ground surface. And then we did what we call stitching to create a full surface map. And these are the real heroes of, in my mind at least, the JWST mirror making story, and that is the technicians. These were the hands people who sat up and ran the grinding and polishing operations. They kept the machines moving 3 shifts a day, 5 days a week. We called it 24/5 operations. And of course, as I mentioned, with the cryo chambers running, they were running for 24/7. So these are my heroes right there. And sometimes the beryllium protocols were stifling. I think I said back in the day to our safety officer that they were inhumane, and it was tough. And we needed to protect ourselves, of course, from this toxic metal, beryllium. But maybe we needed a drink, or maybe even a coffee. We never got to the point where that was allowed out on the optical shop floor. And we were, frankly, promised for years that we're looking into it. I thought we'd get some containers where we could sip some water out of a straw or something like that. But it actually, to be honest, it never happened. And this cartoon shows how third shift might have solved the problem by bending the rules. Of course, this is a cartoon. This never happened. But you can see they've got these coffee straws, so they're able to have their coffee. And as you know, if you've ever worked graveyard or third shift, coffee is the nectar of the gods, and it is a force of nature. And of course, the broader community was certainly tied into our mirror making, especially when we had what we call an anomaly. And depending on the severity of the problem, we could always count on a healthy discussion of the risks and corrective actions soon afterwards. Here we see a discussion at our large conference room table with some, of course, this is a cartoon, a Black Hawk helicopters hovering just outside the conference room. Yes, it was serious, but more often than not, it was, and thank goodness, we almost had a problem. And another thing was critical to this kind of a, if you will, partnership with all of these layers of amazing people was communication. And it was critical when anything that happened unexpectedly. We found this out the hard way a few times, but we refined our techniques, and as I like to say, avoided the pain that had not yet come. And we found out hesitating, that was bad. Skipping a link in the chain, that was also bad. But being honest and open to suggestions, that was always helpful. And many of the senior opticians had, most of our experience, myself included, was with glass or glass ceramics. And beryllium, it was a whole different creature. There were so many difficulties, the toxicity, the micro yield, the pitting, to name a few. But surprisingly, there were a few advantages. With glass, you usually get just one chance at an anomaly, and the glass either chips or fractures altogether. And as I like to say with glass, if the stress exceeds the strength, you get a permanent record of the problem within the glass. Now, my perception is with beryllium, you often get a second chance. It was tougher. And as long as you avoided the thin ribs on the backside, you had a chance of getting to the other side of scary. And yes, there was a secondary. Here we see the secondary mirror, a beautiful convex secondary in the grind. And we see these really paralleled the processing of the primary mirrors. It was much, of course, the area was much smaller, so we spent the predominance of our time on the primaries. But of course, you don't have much if you don't have a secondary. So here's our secondary in the early figure grind sequence. And here we see some early metrology in the grind, and we used our coordinate measuring machine, or CMM. And in the system, you can see the Ruby probe tip that we used for this mechanical measurement. Here, the secondary is on the grinding machine, is skirted, and in the middle we can see of a smooth out grind run. You can see that, and you can note the, as I mentioned, the swarf on the surface. So this is smooth out grind on secondary. And when needed, as part of the processing, hand flipping of the secondary mirror was a manageable task for our senior technicians. And here we see the beautiful rib structure on the back side of what we call the SM. And even in the early grinding, we created the surface figure map as shown here in this colored map. And using the color bar at the right here, we see that the red highs, we can see there's kind of a high edge. We also see sort of a blue trough. Now remember, this is very early, so this don't get excited. This is early in the grind. And you also notice that we see what we call the quilting. You can see those little bumps, or if you will, the surface figure residual in between in the unsupported regions, I should say. And the secondary, it was better suited to a medium-sized polishing machine. Here we see the engineers discussing a run on the SM. And the secondary was really beautiful after we transitioned to polish. In polish, we still made actually some measurements on the CMM, and you can see this polish secondary is on the CMM. But we also had, of course, once it was polished, a Hindle shell optical test set specific to the secondary. And here we have a lively discussion between the process engineers. One of these is me with a different face. And the secondary mirror is, you can see it polishing in the background. And after the gold coating, the secondary was even more amazing in my mind. And here we see some technicians preparing for shipment. And this was actually a modified primary mirror segment container. There's another view of that. Everybody's protecting that mirror, as you can see. And we also had of course, a tertiary mirror. Here we are showing some handling of the tertiary, getting ready to go into the metrology room in that green door behind. And yes, for the secondary and the tertiary, hand flips were part of the process. And here the tertiary mirror, we see it was actually polished on one of those large polishing machines, just like the primary. It was one of the primary machines that we could adapt to polish this tertiary. And we see some smooth out grind. You can see it's in the middle of a smooth out grind run in that right hand image. And then, of course, measuring the tertiary mirror again in the early stages, we would actually employ the CMM, this mechanical probe, and create a surface from that. Here, of course, this is super early. You see a surface that doesn't look too good if you're an optical fabrication person, but this is just to illustrate, you know, what the early figure might look like against the prescription. And of course, here's an amazing shot of the tertiary after it was just removed from the coating chamber, and has that beautiful gold coating on it so that we can get the science that we need. and some further integration of the tertiary. This just an image showing how the tertiary was integrated into some of the structure. And of course, shipping segments. As I mentioned, we needed to get the cryogenic back out, the cryo back out as we called it, and we would have to ship mirror segments to the XRCF facility, and it was a big day for us. You see the tractor trailer, it's a big truck, but we only carried one segment at a time in order to manage the overall programmatic risk. It would be extremely rare that there would be an accident, but we couldn't afford that, and we would put one in a truck, very, very careful, picking the route and so forth, and of course, we would insure them for $30 million each. And then here's, as things progressed and got closer to, of course, flight integration, we transitioned over to these, not a wood container anymore, but these fancy containers. To me, they looked a bit like a reentry vehicle, but they were beautiful. And here we can see several primary mirror segments, in their containers. And again, this is a really beautiful design, and we really treasured and protected these segments. And here we see sort of a bigger picture, if you will, of the mirrors side by side, just to give you some context. As we talked about, we talked through the processing details. Just remember, we've got one secondary, that's the round one there. Of course, the tertiary, and 18 of the larger hexagonal primary mirrors. And here are just some beauty shots. Thanks to NASA and Ball Aerospace, these are just some amazing images, I think. Something to be proud of. Here we have a primary mirror segment, it's gold coated. Amazing. And this is an interesting shot. We see actually, there's actually one segment. I don't know the story behind this, but there's one segment that's of course gold coated, and you see then the bare beryllium segment on the right side. So they're both very reflective. Of course, the gold gives us the reflectance for the science that we need. And here, of course, this is just a beauty shot in the large chamber, and there's of course 6 segments, or I guess 6 segments here. The gaps are not appropriate. These are tested individually, so the gaps in the actual telescope are of course much closer than that. And we see some fiducials. If you know what fiducials are, you can see them here in the images, so that we understand the mapping between the surface and the mechanical. And of course, here is an assembly, if you will, going into a huge chamber. I've never actually been to this chamber. I'm sure Lester has, but this is quite amazing to see.
That's the chamber at in Texas. Where
Thank you.
You're welcome.
And this presentation is dedicated to the Websters, and that is the technicians, the metrologists, and the process engineers. And we built the heart of the world's greatest observatory and devoted ourselves to JWST and the cosmos. So I want to thank you very much, and I'm very happy to share this story. And thank you, and I welcome, if you have any questions, I can certainly try to answer.
Thank you, Glenn. And we'll see if there's only a few people in the room here. Any questions in the room? No. Okay, any questions online? I just want to thank you, Glenn. And really what it comes down to from a manufacturability integration standpoint, it takes a village for the science to work. And I think that's the piece that I took away from this. So I just wanted to thank you and you and Lester for the work you've done in this effort. And on that note, if there's no other questions, anybody online have any questions? I'm looking. Oh wait, there's one chat. I didn't see it.
Maybe Bill has a question. I see Bill's hands up anyway.
Okay.
Yeah, hi.
I'm sorry.
Maybe he's high-fiving. I don't know. Yeah.
Well, the hand was congratulations. The question is, when the micrometeorites impacts happened, can you describe how that felt and what kinds of checks you went through to try to understand what the damage was going to be?
Well, I have to profess my ignorance. I think Lester might know more. I'll
Sure.
tell you what I know, Lester, and maybe you can correct me if I'm wrong. But the micrometeorites are a concern, and they're always available to change the shape of segments. We have limited ability to on orbit to make corrections. We have an ability to do some low order warping of the segments to make some corrections. Of course, very high frequency corrections are not available to us, but the low order things like astigmatism and realigning, if the meteorites hit hard enough, we can realign. Lester, would you like to add to that?
Sure. There's a very detailed estimation of what the distribution and energy is of the micrometeoroids out at L2. And they're also direction dependent. In 2002, I directed some tests where we shot particles at both glass and beryllium samples. This is during the AMSD competition, but those energies were extremely low. A year and a half ago, a micrometeoroid hit one mirror, a mirror C3, and it changed it quite a bit. And they were able to correct that large change. And I meant, if my memory is correct, it was on the order of 150 nanometers. They were able to correct a lot of that by repositioning the mirror. When you move the mirror laterally, it takes out the astigmatism, which was what a lot of the error was. Recently, NASA supported a test of an 8-inch diameter beryllium segment, which was shot with a very high energy particle. The highest velocity that we can get today is about 7 kilometers per second. But if you use a large enough particle, you can get a high enough energy. And that work is still ongoing because you have to use a hydrocode to figure out exactly what the damage is to the beryllium. And then even that small sample, you then have to then extrapolate what that would be to a mirror segment. So that work is still ongoing. So yes, there was an analysis done. There was a prediction of what the micrometeoroids would do, but there are some, it's like a 1,000-year flood. We got hit a year and a half ago with a very high energy particle.
Thank you.
You're welcome.
Thanks, Lester. It looks like we have another question. I think, Jonathan, would you like to ask a question?
Sure. Thank you so much for this. It's truly amazing work. And I'm very curious about tolerances. And clearly you met them. I'm wondering how much you exceeded them, and given all that you've learned, how does that translate into image quality, the ability to see further back in time than we thought we could, or image resolution, things like that? If you could just be a little semi-quantitative about it.
Yeah, I'm going to go based on memory, and I apologize but basically, a lot of the things that we did exceeded the specifications. Surface roughness, because of the nature of beryllium, we were able to get, we can't get quite as good as glass, but we're certainly better than 40. I'm going to say, 30 or 20 on our roughness. In terms of edge roll, we had a requirement of 5 millimeters, but most of our edges were good to, I'm going to say 2 millimeters. So we were much better. The pitting, I mean, we talked about it a lot and we spent a huge amount of time on it, but I mean, you'd be hard pressed to really, see any impact whatsoever in terms of, area lost or scattered light, if you will. Surface figure, we had our 20 nanometer requirement. Very often we were at around, I'm remembering now, and maybe I'm remembering wrong, but maybe about 12 to 15. You had to stop us because, we were passionate about, about making these things as good as possible to get better science. I don't know how much better, the telescope is, but we do have, like you say, there is some ability here to reposition if we get hit, and we can make some corrections if necessary, low order corrections, that is, to further, refine the surface figure of the primary. So I don't know if I've answered your question.
No,
or
that's
if I
very
really...
helpful. A crazy follow-up. Is anyone talking about the next one yet?
Yeah, I think I'm not working on the next space telescope. I think Lester may be more in the loop on that than I am. I know Lee Feinberg's probably already working on the next one. Lester, you got any insights on the next great space telescope?
Yeah, in 2020, the Decadal Committee reviewed 3 very large extensions to JWST, and the proposal that went to NASA basically was to give us some money and we'll do technology upgrades to see if we can really meet where we want, where we want to get to. And as far as I know, they haven't funded those yet, but they're in the pipeline to get those technology developments. One of the proposals, for example, had 36 segments. One had 100 segments. As far as you can go.
Okay. I guess there's questions of launchability at some point, and then obviously the budget might be a limit, although for NASA it's less clear. Thank you very much.
And for ground base, I can speak on that. For the decadal survey, the project that I'm actively involved in right now, the 30-meter telescope. Of course, it's ground based, but it is, fundamentally, in the direction of what we call ELTs, extremely large telescopes. Of course, we have names for all these, size increases. But the ELTs, we got a good one going in Europe, and of course, on this side we got the TMT. Excuse me.
Okay, we have a question in the auditorium here. Stand by.
Hey, I was wondering if you could say anything about how you measure the residual stresses in the mirror, because I think you mentioned that a couple times.
Well,
sure.
Go ahead, Lester. I can tell in a practical sense. Go ahead, Lester. I'll...
So when the segments were still at the Axis Company in Alabama, we did a set of experiments where we created stress-free beryllium discs, and then we imparted stresses to them, and we measured how much the disc bent, and we could tell then exactly how much stress we put in, and we looked at whether we used a sharp tool, a dull tool. So we had a very accurate prediction of how the stresses could be put in. And when the mirror segments were delivered to Tinsley for polishing, there was an estimate for each one of the mirrors separately. And then Tinsley would use their grinding, their schedule to remove the stress that was put in originally. And then they would go to polishing, et cetera, which would put in very little stress. Does that
let me Yeah, let me add a little bit to that. Also, a very interesting and important feature was there was some untouched monuments, a sparse matrix, if you will, on the backside, where, of course, on the backside, these monuments eventually would be bonded to, but they were available to us in a sparse manner. And so we could, on the CMM, if we would put it, backside up, we could touch down on those, I forget how many, maybe there's 18 or so, those monuments, and create, if you will, sort of a global shape, if you will. And then we would monitor that. And of course, we could see if it was, for instance, if you did a grinding run and put some stress in the front surface, and then you measured the delta from the back measurements, you could see that change. So we had an ability to actually measure it because we made available those unchanged monument in a sparse matrix fashion to give us a global shape, and of course global shape change between one measurement and then the other.
Thank you. Any other questions? There was one in chat that I just wanted to read, is how do you maintain a lint/dust-free environment?
Well, now when you say, we at Tinsley, when we're polishing them, we didn't do that. Later on, when they went to the clean room protocols and whatnot, you saw them in the bunny suits and all that. But of course, in an optical shop with, loose abrasive and all the things that we do, it was never considered a clean room, if I'm answering the question.
Okay, great. Thank you. Any other questions? Okay, I don't see any hands raised, so I'm just going to thank Glenn and Lester for their very interesting talk, and I really do appreciate everybody that was in attendance for taking time out of your day to listen to this exciting talk. Thank you so much.
Thanks, everybody, and really glad to share the story. There's a lot of good people that did a lot of good work on these, and it's something I think that we can all be proud of and enjoy. Thank you.